Okay, so we're going to be focusing on composite functions and inverse functions and asking ourselves this question: does it exist? So let's see what I mean. Alright, let's think about the idea of composite functions. They don't always exist. Sure, we can sub one function into another function, but do we get a result that all times, or are there some conditions that are going to define if it exists or not? And that's something what we're going to highlight here today. So looking at this map, we're going to start with two functions, f of x and g of x, and f of x and g of x are fully defined and they have domains which define them. Okay, so let's just say our domain of f is this green circle, which we're going to label x here. So we've got a domain for our f function, and when that gets put into a function and the y values are calculated, it turns into the range. And this is not always the same size. Sometimes that's maybe a little bit bigger than the domain, and it looks like this. So when we are trying to construct a composite function and we're substituting f of x into g of x, then our range that we've obtained from f of x, that needs to fit into the allowed space for our function g of x. You need to imagine g of x having a domain which we are calling y as the box, and we can only put stuff in the box if it's going to fit. Any stuff that is too big won't fit in the box. It's not gonna fit. So it needs to be less than or a subset of the domain of x, of g. So then if this range of f is a subset of the domain, then it works properly. And from there, we're able to then continue on and fully define what is our GOF, our g of f function. And we have this as a way of defining our composite function g of f, where the original domain was all the way up here. The domain for f becomes the domain of g of f. So this is still preserved. Okay, but then we need to think about, once we've developed our composite function, we've defined a g of f of x, what is the range? What is the range we get of g of f of x? So we must consider the range of this function as an independent function by itself across some domain of x, the original domain of f from way up top. So this then becomes the set of x values that is transformed in a different way, and we get our range. Okay, so if that occurs and our original domain fits inside the domain here, then our composite function will exist. So if the range of f is a subset of the domain of g, means it fits inside, it is smaller, then f of g exists. And we can define it fully in this manner. But if it's not a subset, if the domain of x is bigger than the domain of g, then we're in trouble. We get a different situation. So let's consider that. Composite function doesn't exist when we've got this different domain. So let's put him back. Hang on. Get rid of you, put you back up there. All right. So look, here's our domain of G, and it's a little bit bigger. So that's our set of allowed x values that G can have. When it gets put into the G function, it gets mapped into a different set, sometimes larger set, and that becomes the range. So this range now, when we're trying to construct the composite function f of g of x, and we're trying to substitute our g function into our f of x function, we need that range of values to be able to fit in the box. Our domain of f is too small, and so our range of g is not going to fit. It is not a subset. And when that happens, we have to stop, and we are unable to define this function. F of g of x does not exist. So there's no point trying to define something that doesn't exist in the first place. Okay, so let's look at that as an example. So f and g are functions given by these two rules. We've got parabola here, and we've got a square root function. So state the ranges of f and g. Let's have a look. Range of f of x, okay, is all the set of allowed y values. Minimum y value and a maximum y value we have to think about. So if we consider the parabola of the f of x function, then x squared minus 4, that's a parabola that comes down, has a turning point at y equals negative 4, and then continues. And this is for all real numbers. So what range do we obtain from that? The minimum y value is negative 4, the maximum is infinity. So it goes from negative 4 to infinity. Oh, circle bracket, because we can't get to infinity. All right, now what about the range of g? You can write ran for short. The range of g of x. All right, let's look at the function here. This is the domain is all real. Okay, let's continue. So where were we? We're trying to find our range of g of x. So the domain of g of x, as you can see, is all positive real numbers, including the zero number. Okay, so if we think about that on a small Cartesian plane graph of g of x, then g of x is the square root of x, and I know that function behaves in that way. 0 is allowed value, and then all positive real numbers, but not negative. Okay, so our range, as you can see, the minimum g value is 0 and the maximum is infinity. 0 to infinity, positive infinity. Okay, so let's now find part B, find f of g. Okay. So in finding our composite function, first thing we can do is perform this substitution, f of g of x. And we have f is x squared. So if we substitute g of x into our rule, square root of x squared minus 4 gives us x minus 4. Now, it's all very well and good doing that and say, yeah, we've found the composite function, but is that composite function even allowed? So what's the condition that defines whether a composite function exists or not? We have the ran of g of x, the inside function, has to fit inside the domain of f of x. It has to be, we've got some stuff from g of x and we got to put it in the box. If that box is too small, the stuff's not going to fit. So the ran of g of x has to be a subset of the domain of f. So let's check. The ran of g of x is this one. Now, is that a subset of the domain of f? The domain of f up here is all real numbers. So real numbers is a pretty big set, and 0 to infinity does fit inside. Correct. Okay, so then it does exist. Okay. Finally, we can define it fully, FOG, as a function. Now, when we are defining a function, a composite function in full, what do we use for its original domain? If we can see, the original domain of a composite function is the x, is the original domain of the inside function. So we use that. Okay, our inside function is g of x, so the domain of g of x becomes the domain of f of g. Positive real numbers with element 0 goes to the codomain for f of g of x equals x minus 4. Okay? And there we have it. So we've found f of g. Now, how do we state the range? Well, to find the range of this new function here, we have to consider this function across its domain. Okay? This says all positive real numbers, including element 0. So if we were to think what's the smallest possible x value, it is 0. So 0 in this rule here, f of g of 0 gives us negative 4. And then the largest possible x value is up to positive infinity, which gives you a corresponding y value of infinity as well. So our range, or ran of f of g of x, goes from negative 4 right up to positive infinity. There's our range. Okay. So part C says, can we explain why GOF does not exist? And what we have thought about in terms of composite functions is that the range of the inside function has to be a subset of the domain of the outside function. So in this case, GOF, which is g of f of x, the inside function is f of x, so the ran of f must be a subset of the domain of g of x. And if that happens, it exists. So for it to not exist, momento. Okay, sorry about that interruption. Let's continue. Where were we? We're looking at this final part, thinking about does g of f exist? For it to exist, ran of f has to be a subset of the domain of g. For it to not exist, it cannot be a subset. So in other words, this has to be bigger than the box, bigger, and this one has to be smaller. Box is too small to put the stuff in. Let's check the ran of f. The range of f is, which we worked out before, goes from -4 up to positive infinity. Okay, there it is. And we can see that is not a subset of the domain of G, where the domain of G is all positive real numbers, including the element 0. How come? Well, positive real numbers, there are no negatives, whereas here are some negatives. There's -4 up to 0. That does not fit inside all positive real numbers, including 0. Okay? So therefore, our graph does not exist. Okay. So here we go. This is the idea behind composite functions, whether they exist or not. And it's a very crucial aspect because typical SAC and exam type question. So the important thing to draw on is the condition that the range of the inside function is a subset of the domain of the outside function. Okay? Now, gentle viewers, this is something I'd like you to consider that you may think about now. Please try question 6, okay? And we can discuss how you approach that in class.